Hi everyone. So today we're going to go over a couple concepts in exam ASTAM. So first, I'll start off with just credibility. So the entire idea of credibility is how can we measure how credible our data is? How much data do we have in order to estimate a specific parameter? So you could think of this as whenever we have a specific distribution that we're trying to model, let's say trying to model the waiting time for a bus or the waiting time of some event, right? We can model this as x conditioned on some theta. Now, if that theta is also following some certain distribution, for example, x given theta could be exponential, but theta itself is, let's say, gamma, and we have some already observed data that could possibly indicate what that theta parameter is, then that's what we call credibility, is we have this observed data that we can use to actually measure and quantify what the distribution of theta could be. So for example, one of the sort of discrete examples is if we have a proportion of groups, right? We have group one to group three. And each of those groups has a certain Bernoulli probability of committing, let's say, a crime. That could be zero point 0.5, zero point 0.3, and zero point 0.6. So the crime given the group follows a Bernoulli distribution, right? The crime given the group follows a Bernoulli distribution. Now, the proportion of the groups themselves, right, that's discrete. So that is what we call the prior distribution. Group one is 5%, group three is 30%, or let's say group one is 10% actually of the entire population. Group two is, let's say, 80%, and then group three is 10% again. That is what we call the prior distribution. Without observing any single data point, and we had to classify a random person as one of these three groups, then that's the proportion that we would make up. Now, if we observe that this person, for example, has actually committed a crime, then we can now actually shift the proportion that the individual is coming from. So the probability of a specific group, given that an individual has committed a crime, right? That's the new observed data. We can actually adjust our prior distribution to get our posterior distribution. So posterior distribution is essentially the updated prior distribution based upon the data that we have received. And so there are two cases. There's either a discrete version, which we covered here, where we actually have group one, group two, group three as a discrete case, or you could have a continuous case, where instead of having a discrete group one, group two, group three, you actually have, let's say, a parameter x given theta, which follows some continuous distribution. So that's the entire concept of Bayesian probability, is that we have some prior distribution that we have regarding some data point. We receive some observed data points that we can use to actually change our prior distribution to get to a posterior distribution. And so there's many different examples that we can go. First is I'll go over concept of Bayesian. So we talked about x given data follows a predictive distribution. So the reason that it follows a predictive distribution is we already said that x given theta is some posterior distribution, and theta follows its own distribution. Now, once we have received the data, now we can actually come up with a distribution for x given the data, right? So we have x given theta conditioned on the parameter theta. Theta follows its own distribution. But now, because we have observed some data points, we actually can have a distribution for x given the data itself, which is actually ultimately what we want to try to predict. And so one of the ways that you can actually calculate x given the data is you can use the law of total expectation, expected value of the expected value of x given theta given the data. So the first step is find the posterior distribution. How does the distribution of theta change given the fact that we have observed these new data points? And then, now given this new observed data points and given this new posterior distribution, what can we say about the model distribution of x? And so one of the other examples is let's say the number of days, right, an event has occurred in a week follows a binomial 7 with probability theta. Now that theta follows another distribution, right? So number of days is what we call the model distribution, right? Theta, the original distribution of theta is what we call the prior distribution. Now, if we observe that this event has occurred, for example, 3 days, and that is just one observed data point, we can actually now update the distribution of theta. We can have theta given 3 days or given the data that we have already observed. And so that is the idea that we want to try to solve is given these new data points, how can we change the distribution of the parameter, of the conditioned parameter? Now, that's Bayesian credibility. Bowman credibility, what it requires, it instead of requiring the entire model and prior distributions, we actually only want the mean and variance of the model and prior distributions. And we can actually calculate what the expected value of the expected value of x given theta. We can calculate the expected process variance, and we can calculate the variance of the hypothetical mean, all from just knowing the mean and the variance instead of the actual model and prior distribution. And so what this allows us to do is this allows us to actually calculate the Bowman estimate without even knowing the model and prior distributions. We just need to know the mean and variance. And so we have a credibility factor that we assign to Bowman, which essentially states how much weight do we want to give to the empirical observation, which is x bar, and how much weight we want to give to the theoretical observation, which is its complement. So the theoretical or the theoretical value. Theoretical value comes from when we calculate EHM, EPV, and VHM. And again, one of the things to note here is that this value is only for one exposure. This estimate is only for one exposure. If you want to get it for n exposures, you simply multiply it by n. And Bowman-Straub is the entire idea of now, let's say instead of any theoretical distribution, let's say we are only working with empirical data. Let's say we only have actual observations and we have no idea of the theoretical distributions that these observations are actually coming from. Now, how can we get an estimate even from empirical data? That's where Bowman-Straub actually comes in, where it provides formulaic approaches for these different estimates to get to a theoretical estimate. And so that's the difference between Bowman and Bayesian, which we consider to be theoretical, driven from theoretical distributions. And now we're transitioning that over to more empirical data or Bowman-Straub, where we're able to actually get these values, get these estimates from just empirical or observed data without requiring the need for any theoretical distribution. One of the things to note is that Bowman credibility and how that relates to Bayesian is Bowman credibility is the least squares estimate of Bayesian credibility. So you can think of this as if you're trying to estimate, Bayesian credibility, Bowman credibility is just the least square estimate of that. So you can think of this as you're essentially fitting a line to the estimates of Bayesian estimates. So it's the linear approximation to Bayesian credibility, right? It's the least square estimates. And this is the optimization function or what it's trying to minimize, or the loss function, what it's trying to minimize. And so one of the things to note about Bowman, the relationship between Bowman and Bayesian, is that there will always be Bayesian estimates that are above and below the Bowman line. And that's because the Bowman is the best linear approximation of Bayesian estimates. It is always going to be a linear function. So if it's a linear approximation, it only makes sense that the Bayesian estimates are both above and below the Bowman line. So that's one of the key things to note is what's the relationship between Bowman and Bayesian. And now one of the other things that would make sort of solving for the posterior mean a lot easier is if we know that the prior distribution comes from some parametric family of distribution, specifically if the model distribution is in the linear exponential family, then we call the prior distribution a conjugate pair of the model distribution. So one of these examples is Poisson gamma, binomial beta, exponential gamma. There's other pairs like this. When you recognize this pair, you can automatically skip the integration and you can get to the mean, the posterior mean, using an assumed distribution. So for example, if you have x given lambda following a Poisson distribution, where lambda follows a gamma distribution, the posterior will be gamma and the parameters will obviously be shifted. But you don't actually have to go through the entire uh, process of calculating the probabilities. You can resort to this posterior distribution. It's going to save a lot of time actually on the exam. Next, we have empirical Bayes with uniform exposures and then empirical Bayes with non-uniform exposures. So again, this is referring to observed data points, but whenever we have these observed data points, we may not have uniform exposures. And of these data points? So what do I mean by uniform exposures? Let's say if we have policyholder 1 and policyholder 2, and policyholder 1 is only actually observed for 2 years, and policyholder 2 is actually observed for 3 years. So that's the first basis of exposures. We don't have the same amount of data available for each of these policyholders. So that's the first. That's actually only the first level of identifying if something is uniform or not, is the number of periods that each of these groups are actually observed. So if that differs, then we don't have uniform exposures. We have non-uniform exposures. The second is if the underlying metric for measuring exposures differs by year or by policyholder. So what do I mean by this? Something could be like, let's say the number of claims, right, for policyholder I and policyholder 2 in a given year. Let's say it's 6 and 12, but the exposure for policyholder 1, let's say I guess the number of vehicles is 4 compared to policyholder 2, number of vehicles let's say is 6. So that's a different exposure basis. So that's what we call non-uniform exposures. Is we have policyholders or we have a group uh, of policyholders, but the basis upon which we're getting their either claims data is actually different. So in the example that I gave, the number of vehicles is the exposure unit, or the number of vehicles per year is the exposure unit, and that's fundamentally different between these two groups. So that's the second element from which we can detect if this data is actually non-uniform. And then we also have semi-parametric empirical Bayes, which is the idea that, okay, we have some theoretical distribution and we have some empirical observation. How can we combine these two to get to a better approximation of what the predictive mean could be? And so for Poisson, one of the properties of Poisson is that the mean equals variance. So we know the mu hat is going to equal v hat. The expected hypothetical mean is going to equal the expected process variance. And so whenever we have these special properties that we can use, that's what we refer to as semi-parametric empirical means. We can also have the same property for gamma and for a lot of these other distributions that are non-Poisson. But essentially, it comes down to the fact that we can use mu hat and v hat in some formulaic manner. So that's semi-parametric empirical Bayes. Now, if we go to, let's say, construction of parametric models, which is another topic, this is the first section dives into the idea of maximum likelihood estimation. So the entire concept of this is we're trying to determine a population parameter, let's say theta, right? We're trying to determine some population parameter theta coming from some right theoretical distribution. Now, if we already have some observed data that we have, let's say we're trying to get we know that this population is exponentially distributed with mean theta. Now let's say we have some observed data that we have, right? Let's say we have like 50 different samples. What is the best approximation from those samples of theta? And how can we get to that best approximation? Well, that is where maximum likelihood estimation comes in, is we're trying to maximize the log likelihood function, right, based off of the samples, based off of empirical data. And so from this empirical data, what's the highest likelihood that this parameter can be, right? Right. So what's the greatest likelihood of this parameter being 2 or being 5 or being 6? So that's the number that we want to assign to this parameter. So that's maximum likelihood estimation. Now, there's also method of moments. Method of moments is common when we know that the MLE actually depends on the sample mean. So for Poisson, we know that mean equals variance. For gamma with a fixed alpha, you can get the mean, the sample mean, to equal to the expected value of x. So that actually you can put that in terms of the sample mean. Also, normal distribution, binomial with fixed m, negative binomial with fixed r. These are all common distributions where the MLE depends on the sample mean. So you can use the sample mean in some formulaic fashion or manner to actually get the maximum likelihood estimation for that distribution. And then let's go over a couple of the different tests to actually assess model fit. So first is chi-squared test. Chi-squared test is all about determining the difference between your expected counts and your observed counts. So if you have these different discrete groupings, you can get what's the expected number of counts for these groupings, and you can get the expected number of counts by, you will typically have like a theoretical distribution, like a Poisson or exponential, and you can apply that distribution to the groups to get the expected number of counts in each group. So for example, if we know that this follows a Poisson distribution, right? This follows a Poisson distribution, and we have these discrete categories, let's say 10 to 20, right? 21 to 30, and then like 31 to like 50. Let's say we have three categories, and we have observed number of counts in each category. This is the raw empirical data. Now, how do we get the expected number of counts? Well, we know that theoretically this follows a Poisson distribution. That's our null hypothesis. We're trying to test, does this data actually come from a Poisson distribution? Well, that's where we get, if it were to come from a Poisson distribution, what is the expected number of counts that we would have in each of these different intervals? And so that's where we say, okay, what's the probability that x is between 10 and 20 based upon the fact that this is coming from a Poisson distribution? And then multiply that by the total number of counts, you get the expected number of counts in that should be within this interval if it's coming from a Poisson distribution. So that's where we have the expectation and the observed. And then the chi-squared statistic is the sum of the expectation minus the observed squared over the expectation, and that's our statistic. Chi-squared test is statistic, and if that's greater than some critical value, we can reject the null hypothesis and say that, hey, there is significant difference between the expected number of counts and the observed number of counts, so we can safely reject the null hypothesis that the data actually doesn't come from this theoretical distribution. It's not a good fit. The model is not a good fit for this data set. So that's chi-squared, one of the ways to evaluate the fit of a model. Second way is through, we call it Kolmogorov-Smirnov test. And what we do here is we compare the fitted CDF, so the actual CDF, versus the actual theoretical CDF with the empirical CDF. So we have the empirical CDF, which is based off of the empirical data, and we have the theoretical CDF, which is based off of the theoretical distribution. If we notice a significant difference between these, then we know that the model is not a good fit for the data set. So how we actually go about getting the test statistic for this is for each observation. So let's say we have n observations, 1 through 10, or yeah, let's say we have 10 observations. For each observation, we're going to get the empirical CDF from both the peak and the valley. Peak refers to if it's just strictly less than that number, and valley refers to if it's just strictly less than the number. And then peak refers to if it's less than or equal to that number. So that's the empirical CDF. You get those two estimates, or yeah, those two values from the observed data. And then we have the fitted CDF, which is the actual theoretical distribution. So you actually take the integral or you evaluate the CDF, and then you get, okay, what is the probability that this x is less than or equal to some value? And now the max of the difference between one of the valley and the peak empirical fitted CDF and the theoretical fitted CDF, that is your test statistic for Kolmogorov-Smirnov test. And if that test statistic is larger than some critical value, we can safely reject the null hypothesis and conclude that this model is actually not a good fit for the data. And then we also have, actually we'll go over, yeah, chain ladder as well. We have chain ladder as well. So typically when we are reserving amounts to develop and pay out claims, right? We only have some observed data and we want to project in the future how much reserves we would need to have to actually pay out these different claims. And so that is what we refer to as reserving. And one of the ways that we can actually do that is through what we call chain ladder. Actually, I'll go through this later. Just want to give a high level concept of what this actually is. So chain ladder is essentially the idea that we're going to use historical development factors to project out the number of reserves or the amount of reserves that will have to be made for each development year. So high level example is for development year 0, from the historical average, we've noticed that it's like a 1.2 factor. For development year 1, we've noticed on average, it's around like a 1.4 factor and so on. We apply these historical development factors to project future, right, future claim developments. To project future claim development. So that's just one of the ways. And one of the things about chain ladder is actually it only uses historical data. So when we go later into BF method, we'll see that it uses a weighted average of the chain ladder estimate as well as the prior estimate, which is some industry data. So it actually has some balance between both industry and historical data. But chain ladder is strictly historical, just uses the past development factors, what it has seen and observed in the past to project the future. So these are just some initial concepts of ASTAM that I wanted to go over in this video. I'll see you in the next video.